And there's the tube. Okay, so we're going to talk about the first 6 weeks worth of astronomy in 30 minutes or less. Ready, set, go. We talked about a lot of stuff. We started off by taking a look at the sort of definitions of astronomy. We looked at ancient astronomers, ancient civilizations. So you are going to need to look back through those. And big ones that you need to take a look at are civilizations like the people at Naphtali in Egypt. The Egyptians that built the pyramids, ancient Babylonians. Excuse me. Ancient Native Americans. Was it Chocolate Canyon?
Yes.
Okay, and then like South Americans that built Chichen Itza. Okay, Chichen Itza. At least sort of know who they are and what it is they made. And then be sure you've got a good grasp on the arguments between it being a heliocentric or a geocentric system, and why people, before they had more data, believed that we were the center of everything. The video you watched yesterday was really doing a nice job of getting into that. Okay, I'm really enjoying those videos, but I'm a teacher, so we took some extra time and took a look at some of the ancient Greeks, and so you need to kind of know specifically these five right here and the contributions they made. Aristotle, I believe he was one of the first to take a rational view of the cosmos and not just try and say, hey, a god or a demigod exists. Reasoning out, physical phenomena that dictated what we see in the heavens. Of course, he was wrong about a lot of it. He thought that the Earth was the center of things because we couldn't really see the stars move in relation to what we saw. Aristarchus was one standout who believed, hey, it makes more sense for the sun to be at the center of things, but nobody listened to him. Eratosthenes, do you remember what his big thing was? Measuring the circumference of the Earth by looking at the comparison and the shadows at the same time in two different places. Hipparchus, don't exactly remember what Hipparchus did. Okay. It was good to know, but it's in the slideshow. And I do have links to all the slideshows in the very last slide of this. So, and then Ptolemy is the last one we talked about as being quote unquote ancient, even though he was around 100, 150 AD. And he lived in Greece, but he was technically a citizen of the Roman Empire. Ptolemy is the big one who mathematically worked out a model for the solar system that took into account retrograde motion of planets. He came up with these things called epicycles. And so while everything was going around the Earth, the planets were actually also on circles, which explained why they seemed to kind of back up and then go forward again. And again, his model was the one that most people worked from for about 1,000 years. So, he was wrong, but he did wrong very well. Then, of course, the Middle Ages hit, and you had, the fall of the Roman Empire. You had all sorts of tribes running through and burning things. They burned the library at Alexandria. And so learning a lot of this knowledge, the old stuff was being saved and taken care of by monks in monasteries. And then other stuff that was really going on was actually happening like in the Arab world, and of course China and India. You still have developments going on in astronomy. Later astronomers that you need to know about, first big one that we talk about being a modern astronomer is Nicholas Copernicus, who was one of the first modern ones to resurrect the idea that, hey, it actually makes more sense if the sun is at the center of things. He waited until he was very close to death, or after his death, to publish his great work because he didn't want to argue about it. That's like way before Facebook. If instead of Facebook you just put your you put your opinion out there and then you died, you didn't have to read comments. I can respect that.
It's a long wait to block someone.
Right. Yeah. Tycho Brahe, the Dutch astronomer, he tried to combine the heliocentric and the geocentric model by suggesting that, hey, while everything revolves around the Earth, all the other planets actually revolve around the sun. And to him, that made a lot more sense than the epicycle. So he was not quite right, but he was getting warmer. Kepler discovered that the motion of planets in their orbits only makes sense if you consider that those orbits have to be elliptical instead of round. He also figured out that if you have something orbiting, it moves faster as it is close to the thing that's orbiting and slower as it's further away. Galileo was one of the first ones to really make big systematic observations of the sky using telescopes and then writing about it. He was one of the first ones that we know that made detailed observations of the moon's surface, craters. He also discovered the 4 biggest moons of Jupiter, which are called the Galilean moons. He published a work where he said, hey, the sun is at the center of things, and he didn't do the gracious thing and just up and die about it. He instead stuck around. So we had to deal with that kind of heresy by locking him up in this house for the last decade of his life or so, where he continued to write and make observations. Like most nerds who get locked in, he was pretty happy with the social distancing thing that he was imposed on him. And then Isaac Newton came along and built on the shoulders of all these folks and did some brilliant math, and he conceived the laws of motion. He also conceived the the law of universal gravitation, which says that gravity is a force that is between any 2 bodies, and that is determined by how massive those bodies are and how far apart they are from each other. And it applies everywhere. And so we kind of stopped off with him looking at old history of astronomy. We're going to pick up from there in the coming weeks when we start looking at more discoveries and exploring space around us. But before I move on from this slide, does anyone have any questions or anything to clarify? Okay. Let's talk about constellations in the night sky. We looked at a slideshow over constellations that had a lot of really humorous spelling mistakes. We figured out how many stars were in the night sky, for instance. But we did learn that the definition of a constellation has changed through time. Constellation used to be just what was a name given to a cluster of stars that people kind of did connect the dots and figured out, hey, that looks like a lion, or hey, that looks like a guy wrestling a snake, or whatever it is that they look like. A modern definition of constellations, what they call constellations, to a large degree we call asterisms now, just recognizable shapes. A constellation is a region of the sky, and how many of them are there?
88.
88 modern constellations, good. When we're here on the Earth, the stars appear to sort of wheel and spin around us. And of course, that's not because the stars are spinning, that's because we're spinning. But, it's like, what's the point of having an argument with the sky? It's not going to argue back. So, from where we're standing, it looks like the stars sort of spin. There's one star, if you're in the northern hemisphere, that looks like it's at the center of the spin, and everything else is just sort of rotating around it counterclockwise. What is that?
Polaris.
Polaris, the pole star, exactly right. And it will be the pole star for at least, the next few thousand years. Constellations are useful not just in mapping out where things are in the night sky, but also they're useful in navigation. They were useful to ancient civilizations in determining a calendar, time of year. If you could see such and such constellation when you knew that it was about to be the rainy season, or it was time to plant your crops, or whatever. You also built and used quadrants to take angular heights of things. You took the angular height of the building and did a little bit of math with triangles and figured out a pretty good estimation for the height of that building. You also took a quadrant and used it to get the angular height of Polaris, which is a pretty good way of estimating your latitude. Okay, and some of y'all got pretty close to that. It's important that you know certain recognizable constellations. The ones you're going to need to know are the 12 zodiacal or seasonal constellations, as well as Orion, both Ursa Major and Ursa Minor, Cygnus, and Cassiopeia. Okay. Now, you made flashcards for those. Please study your flashcards. On this next slide, I've got the 12 zodiac constellations in a slightly different way than you probably got from one of the flashcards. But there's enough commonality there that you should be able to look at one and look at the other and say, oh, yeah, that's what I do. Okay. Some more than others, but you need to be able to, there will be questions where you have to identify a constellation. Questions? We are getting through this pretty quick because you guys don't have questions, and that's fine. We spent the last week or so looking at the Earth, Moon, and Sun, and all the ways that they interact with each other. Latin names of the Earth, Moon, and Sun. Who knows them? Parasol and Luna. Parasol and Luna. Very good. Okay. We need to talk about different ways they move. Of course, I mentioned when we were looking at the checkpoint a minute ago, rotation is spinning on an axis. Revolution is actually revolving around another body of some kind. Need to know the effects that they have on each other. Of course, one of the biggest effects that the sun has on us, as well as the rest of the planets in the solar system, it is the source of light and heat energy, and without it, we would not have life on this planet. Right. Because it provides light energy and heat energy, and one, it keeps us from freezing to death. Two, it gives plants and other producers a way to make food the rest of us benefit from. It's also responsible, along with the tilt of our axis, in the seasons. Now, I've got this picture right here in the middle. It's from one of those other slideshows that you've got in your drive. But I really like it because it does a good job of showing the how the tilt of the Earth doesn't change. It's always pointed towards Polaris. But as we revolve, the sun's rays are striking us at different angles. And so right here, this is happening right around June 21st. I don't know what happened right there. That was weird. So that would be the summer solstice. This right here is happening right around December 20th or 22nd. That's the winter solstice. And then, so this right here would be the spring equinox. This down here would be the fall equinox, when light is shining directly 90 degrees overhead if you happen to be on the equator. It's also called the equinox because equa means equal, nox means night. Okay? So it means that the hours of night are equal to the hours of day. You get 12 hours of each on the equinox. The word solstice actually comes from sol, which means sun. And I'm not sure about stis, but it literally means the sun stops. So if you have been watching the sun and its apparent movement across the sky from east to west, you notice that it gets higher and higher and higher, and then there's a point where it stops and it doesn't get any higher. And then it starts getting lower and lower and lower until it stops getting lower, and that's the other solstice, and then it starts getting higher and higher and higher again. Okay? Again, the sun's not moving. We are both rotating and revolving, so it looks like the sun's moving. It's all about the apparent motion. The tilt of our axis is around 22, 23 degrees. Okay, and that never changes. It does wobble just a little bit, but the wobble happens so slowly that it really does not affect things too much for us. I think it's really important to talk about the ecliptic. So if you've got the sun, and here it is, if you imagine that the sun is sort of being bisected by a big plane. Okay, and the Earth is set down inside of that plane. Okay, and the other half is underneath it there. Our orbit is elliptical, and it takes place within that plane, and that's what the elliptic is, or the ecliptic, I'm sorry. Pretty much every planet in our solar system is on more or less the same plane with us. There are a few that are slightly out of tilt, but for the most part, they all follow the same sort of flatness. One of the big reasons why Pluto got kicked out of the Planet Club about 10 years ago is because his ecliptic was all wonk. It was definitely not in line with everybody else. Sometimes his orbit even crossed that of Neptune, so he was closer than Neptune was. You know, some people just don't know how to behave, so you kick them out. You know, no hard feelings. Don't be a punk in my house. And I like this other diagram down here because apparent movement of the sun, it's a really good way to kind of symbolize, you know, how it looks at different altitudes depending on the time of year when it reaches its apex. Questions on this one? Would you believe we're almost done? We do need to talk about the moon. So I've got this whole slide here kind of devoted to the moon. You need to know the moon phases. You need to know what order they come in. You need to know if it is waxing. That means that it looks like it's getting fatter. So the moon is waxing from right here at the new moon up until it hits full moon. Okay, and then it's got about as fat as it's going to get. From that point forward, it's now waning. Okay, it looks like it's going away. So from here forward until it vanishes completely, it looks like it's getting skinnier and skinnier and skinnier. Zenith versus apex. Zenith is right overhead. Apex is just the highest point in an apparent path that something will move, whether it's the sun or whether it's the moon, whatever. We talked about how the moon and its position affects tides. Okay, you have 2 high tides and 2 low tides in any 24-hour period. Okay, roughly 6 hours apart. They don't all happen at the same time every day because while the Earth is rotating at about 15 degrees an hour, the moon only revolves around 13.5 degrees a day. So every day, if you go outside at the same time, the moon is going to be in a slightly different place at any given time. The side that the moon happens to be close to, or the opposite side that the moon happens to be close to as the Earth is rotating, they bulge. Okay? The moon's gravity sort of pulls them out a bit, so you have high tide when you're in line with the moon. When you're not, you have low tide. Especially high tides, called spring tides, happen when the Earth and the Moon and the Sun are all in a nice line with each other, and especially lower tides, called neap tides, happen when they're kind of perpendicular. We talked about solar lunar eclipses. Let's talk about umbra and penumbra. Okay, these are some great words. So if we're having a solar eclipse, right? So the sun is way out here, shining all of its sunlight. The Earth is doing what the Earth normally does.
How long does it take for the moon to fully cycle around the Earth?
It's about 27, 28 days. About a month. 4 weeks. So what's happening here is that the sun's light is being blocked at a specific point on the Earth. So there's a point right here where if you're standing on this point, it looks like a big eyeball, then it's going to look like the sun is being completely covered by the moon. You get a total eclipse. We call this little cone of complete and total darkness in here, we call that the umbra. Okay? There's still going to be a region around that, though, looks even more like an eyeball, where there's going to be some shadow cast, but it's not going to be completely, wow, very eyeball. It's not going to be completely covered over, it's just going to be partially covered over. We call that region in there the penumbra. The way that I kind of remember the difference between the two, I think umbra, I think umbrella. Okay? If you're right under it, you're under the umbrella, you're in the umbra, you're not getting rained on. If you're kind of off to the side, you're still going to get wet. In that case, you're still going to get some light from the sun. I don't know if that helps anybody at all, but it's a thing, so there you go. When you got your packet of moon gazing stuff, the last page on there shows some of the geographical features of the moon. You need to probably know some of those. You'll probably see a question saying, which of these is not something you would find on the moon? And if you have given that a glance and are kind of familiar with it, then that shouldn't be a problem. Okay. And I think that takes us to the end. Like I said, the very last slide on here has clickable link. Wow, that's wacky. Has clickable links to all the different presentations that all of this stuff is taken from through the last 6 weeks or so. So if you've lost track of any of those, you can click on them and listen. Does anyone have any other questions? Okay. I'll get this video chewed up this afternoon and get it posted.